So welcome to episode 18 of the Probability and Statistics for Engineers. I am Mohammad Momenzadeh and this is the episode 18 of our lecture. Previously we discussed about the type of the distribution, some discrete distributions. We discussed about the binomial, multinomial, and also hypergeometric distribution, and we discuss about the distinguishable character between this type of the distribution, and by one example we determine that type of the differences between these distributions. So today in this lecture we will discuss about the remaining part of the discrete distribution, I mean the geometric distribution and Poisson distribution as well, and in the meantime we will discuss about the approximation cases as well. So let us start our discussion by the similarity of the hypergeometric distribution and binomial distribution, and use one of them to approximate another one as well. As you can see in this slide, we have the relationship between the binomial distribution and hypergeometric distribution. And there is an interesting relationship between these distributions. If n is small compared to capital N, the nature of the n item changes very little in each row. So let us take a look on the situation precisely and see that what do I mean by that things. So in a hypergeometric distribution, as you remember, we had a resource of a data or objects that we split it to two parts. One part is a favor part that has k objects, and the another part has capital N minus k objects, which is not our favor, and it's actually considered as a failure cases. So if the total number of the objects is capital N, and we draw small n numbers of the objects from that resource, means that the objects that we draws from there is small n, then as you remember that if the replacement is allowed, or if the nature of the objects is not changed that much, or it's not considerable, the changes in the nature of that object, the draws object, then we can assume the hypergeometric distribution as a binomial distribution. So over here we have two cases for each of that materials or each of draws, and one of them determined by the success with the probability of P, and the another one with the Q. And if the replacement is allowed, as I said it, the probability of P is given by K over N, because we have K favor objects out of the capital N, and the nature and the value of Q can be evaluated by 1 minus P or N minus K over the capital N. So of course this one is as the same as 1 minus P as well, so you can write it as 1 minus K over capital N. So in this case, the if the value of n, the capital N, is bigger than n, and this value is considerably bigger than n indeed, by the in other words, we can say that n is small compared to the n, the capital N, considerably small indeed. Then as you can see, this correction coefficient as well approximated by 1, and we can say that the given actually distribution has a nature of the binomial distribution, and instead of using the hypergeometric distribution you can use the binomial distribution to calculate the probability. So let us take a look at one example to see that how can we approximate this value. So here we have one example about the given situation. In this example, a manufacturer of automobile tires reports that among a shipment of 5,000 tires sent to a local distributor, 1,000 are blemished. So means that we have a resource of tires over there that contains 5,000 tires inside of it. 1,000 are blemished, so I can split that actually value or that resources to two parts. 1000 are blemished and 4000 are the simple cases. So if one purchases 10 of these tires at random, means that we select only 10 items or 10 tires of the cases that we talk about it. Let me just sketch one tires over there. So it's assumed that it's a tires, and we have actually this tire over here. Up to 10 number of them are selected over there. So what is the probability that exactly 3 are blemished? So I want to know that what is that probability. So let us take a look at the value of the resources and assign the value for that one. So of course the capital N is 5000 because we have 5000 objects in our cases, and k is given by 1000, the n minus k is given by 4000, and the small n is 10 cases over there. So as you can see, this small n or 10, n equal to 10, is too small in comparison with the capital N that we have it. I mean, the capital N that we have it over there is 5000, and it's too small in comparison with that one. It's considerably small in comparison with the value of a total. So because of that, we can use the binomial distribution to actually approximate this value. Indeed, the exact value of the cases that we have it, the probability of x equal to 3, x is the number of the blemished tires. So the value of x equal to 3 is as follow, the exact value. It's gonna be the denominator is a selection of 10 tires out of 5000 cases that we have it. As you can see, that number is too big, and to calculate it you need a good calculator indeed. And this will be 3 out of the blemish cases that we want it, because we want exactly 3 blemish one, means that 3 should be chosen out of 1000, and the remains one means that 7 should be chosen out of 4000. And if you want to see that what is that number, I just take a look at the denominator of this one, or the numerator as well. So if you just take a look on it, for example, only this part that we have it is a 5000 times 5000 times 4999. So it's gonna be a big number at the end when you just calculate all, and it's going up to 4990 90 actually, because we have 10 cases over here. So, and we should divide that value by 10 factorial, means that 10 times 9 times 8 times 7 up to 1. And as you can see, this number is too big, and calculating of this value is not easy. It's impractical. Instead of calculating that one, we try to actually approximate this value by the binomial distribution. If we use it as a binomial distribution, then it will be the selection of 3 out of 10, because we have 10 cases that we are looking for 3 successes, and the probability of being blemished is gonna be simply 1/5. So as you can see, the probability of the favorite case or the blemish case will be 1000 over 5000, and the differences between this value for the different draws is not that much big. It's not considerable indeed. So it will be 1/5. We can assume that it's 1/5 for all. It's as the same as replacing back them and again choose them and draw it again over there. So 1/5 to the power of 3 and 4/5 to the power of 7. So as you can see over here, calculating this value is easier than calculating the previous one. So by the another word, we can take a look on this situation at the solution. and the results will be calculated easily by this value, and it's going to be 0.2. As you can see, the hypergeometric distribution with that factors can be approximated by the binomial distribution. So this is the approximation of hypergeometric distribution by using the binomial distribution. So at the next slide, we are looking at the geometric distribution. First of all, let us take a look at the definition and the description of this distribution that we have it here. The geometric distribution. This is an example of a waiting time problem. That is, we wait until a certain event occurs. We make the assumption used in the binomial distribution. So assume that. So look at it, at the geometric distribution we have the similar assumption that we have it for the binomial distribution. One of the best example for the geometric distribution is shooting some type of the animals with the gun and see that what is the probability at the end. Let me just put the example, then we return back to that definition. For instance, assume that I have a gun. It's not a good idea to kill the animals indeed, but we just use this definition and this example to determine the situation. So we have a gun that we try to somehow hunting the or shooting to the actually birds that we have it over here. Assume that I try these shooting cases for many birds over there. So the number of the birds over here is infinity, means that we have a lot of experiment over here or a lot of trials over there. So the probability of shooting correctly, I mean shooting and targeting exactly the birds, is 0. For example 7 in this case. That person is an expert in shooting to the birds, for instance. So the probability of getting wrong is 0.3. I mean not targeting that type of the birds, and assume that this value remains constant for all cases over there, means that it's as the same for the second shoot and the third shoot and so on. Means that we have this situation over here. For the third bird we have the same probability, and it's going on up to the end. I mean, we can just keep that number correct for all cases that we have it. So the question over here is about these things. Let me just put it over here, means that it's correct for all birds over there. So what is the probability to get the first shoot at the fourth try, for example? So over here we have the binomial experiment. Why it's a binomial? Because some statistical experiment over here shooting to the birds is repeated n times, and n is not actually clarified over here. So n is some number that we try to shoot to that birds. And in each trials we have the independent cases, means that shooting to the first bird is independent from the second one and so on. And the probability of the success over here, means shooting and hit that bird, is 0.7, and it's constant for all cases over there. This is our assumption. And the failure over here is not hitting that bird, and it's 0.3 for all birds in that sequence of the animals that we consider it over here. So up to here everything is as the same as a binomial distribution. The only differences is about the x or the random variable. X over here determine the number of the trials. So over here x is actually denotes the number of trial that we get success. So that means the first success. Indeed it's better to mention that, emphasize about the first success, to get first success. So what do I mean? Means that, for instance, if I just say that what is the probability of x equal to 4, I'm not looking for the number of the successes. The number 4 over here determine the location of the success. Means that not in the first location. If it's a first location, then we have the second one, then we have the third one, and the fourth one as well. Third one and the fourth one is a case that we are looking for. Means that I want to get the first actually success in the fourth one. By the another word, is as the same as this probability of x equal to 4, for example, over here is as the same as the probability of getting the failure at the first try and getting failure at the second try. Let me just denote it by F2, and getting the failure at the third try and the success at the fourth try over there. So when I just talk about the probability of x equal to 4, means that I want to have the failure at the first, second, and third case, and at the end we are looking for the first success at the fourth try. And because there is an intersection between them and they are independent, this is the binomial distribution indeed, so it will be as the same as a probability of getting failure at the first one times, because the intersection will change to the multiplication of the probability if the events are independent. So it will be the probability of F3, means that the third one will be failure, times the probability of success in a fourth place. So it will be the multiplication of this probability. And of course, because the probability of failure is as the same for all cases over there, so it's q times q times q, or q cube times p. This is gonna be the probability of x equal to 4. By the another word, we can extend this idea to the general cases. Means that the probability of x equal to small x will be equal to the probability of failure in that binomial experiment to the power of x minus 1 times probability of p, and this determine the probability distribution function in this case. So as you can see over here, these are that 4 items determine the binomial distribution property over there. So as you can see over here, on each trial of our experiment, the result is one of 2 outcomes, success or failure. So up to here, each of them has 2 cases, means that we have a success or a failure, as you can see over here. The second one is the trial are independent. The third said that the probability of success at any trial is p, so that the probability of success are p, and consequently probability of f as a failure as a 1 minus p equal to q. So this value is constant, it's not changed like a hypergeometric distribution. The random variable x denotes the number of successes in n trials. The last item is a actually character of the binomial distribution, which is not correct for the geometric distribution. Indeed, we have the random variable x over here as a number of the trial that we get the first success, while in the binomial we have fixed number of trials and a variable number of successes. In the geometric distribution we wait for a single success, but the number of trial is variable. So this is the differences between the geometric and binomial distribution. A perfect model of the situation is tossing a coin loaded so that the probability of a head on a single toss is p, and q is getting the tail as well, until a head appears for the first time. Means that you toss the coin 1 times, 2 times, 3 times, 4 times, up to get the first actually head. For example, over here the success is head, and for this situation also we have the same thing. About the expected value and variances of this distribution, we have the following discussion as well. So to calculate the expected value and the variances of the geometric distribution, we have the following discussion. So at the orange box, you can see the quick review of the geometric series. If you remember from the calculus 2, we have the geometric series as well. So let me just write it here, geometric series. So if you consider the terms of 1 plus q squared, q plus up to q to the power of n, or summation of I equal to 0 up to n of q to the power of I. This is the notation that we can use it for that summation. Then by multiplying these terms by 1 minus q and divided by the same terms 1 minus q in a condition that the q is not equal to 1, by multiplying the terms 1 by 1 by 1 and then subtracted when q multiplied by this term, you will reach to this actually expression. And after cancelling the similar things means that q is cancelled by minus q at the multiplication of q by that terms, and so on. You reach to 1 minus q to the power of n plus 1 over 1 minus q. And in a case that absolute value of q is less than 1 and tending n to infinity, you will find the value for the geometric series. You know this formula from the calculus 2, means that summation of q to the power of I is 1 over 1 minus q. And right now, by taking derivative from this expression respect to q, then the derivative of this series at the left side is I q to the power of I minus 1. At the right side, it will be 1 over 1 minus q squared. Indeed, that 1 minus q at the denominator can be written as 1 minus q to the power of minus 1. And if you use the chain rule to calculate the derivative, you reach to this expression that you can see over here. Why we did this type of the things and calculate this expression? Because to calculate the expected value of x, we should multiply the value of a function xi by the probability, and the value of the function is given by I, and the value of the probability is q to the power of I minus 1 times p. Then the expression, this summation over here, is equal to 1 minus q square, and p is not related to the I, so it's coming out from that summation. So then we have p times this expression, and 1 minus q is equal to p. So we have 1 over p squared times p, that reach to 1 over p. So the expected value for that geometric series is 1 over p, and the variances will be 1 minus p over p squared. You can calculate the variances as well with a similar discussion. You should calculate e of x squared for that case, which actually lead you to this expression that you have I squared times the probability that we have it q to the power of I minus 1 times p. And again, you should use the similar discussion by taking 2 times derivative of this expression. You can lead to that variances. Indeed, at the geometric series, we can have the following things as well. Let me just sketch the situation over here. So as you can see over here, for the geometric series, for the geometric distribution, indeed, we have the infinity numbers of the terreals. It can be any terreals that you want it. I mean, it's going up to infinity. And when we discuss about the x as a random variable, x determine the location of a first success. So the probability of getting the first success is equal to p, because the probability of the success is determined at the question by p. The probability of getting the first success at the second try will be p times q. As I said, it's happened because we want the success in a second try, means that the first one should be failure and the second one should be success. And because we have the independent terreals over here, the q should multiply it by p. We can use the multiplicative rule, and over here it's going to be p times q. And for the third case, means that if I want to have the first successes at the third terreals, then it will be p times q square. It's like tossing the coin and getting the first heads. I just use that type of the statistical experiment over here, and schematically I just describe the situation by that diagram. So at the x case, when I'm looking for the first success at the x place, it's going to be p times q to the power of x minus 1, and this is the probability distribution function. Generally you can see it over here that simply the addition of this probability means that if you want to add all of them together, the result will be equal to 1, because it's if you factorize p, the result is 1 plus q square up to the end, and this part is a geometric series as I said it in a previous slide, and the equal values is equal to 1 over 1 minus q, and 1 minus q is p, so p and p will be cancelled and the result is equal to 1, as you can see over here. Let us take a look at some example to see that how can we deal with this situation. So we have one example over here about the geometric distribution, and you can see that example. A shooter has the constant probability of 0.4 for hitting the target. Means that if this is a target, for instance it's a bird that we can consider it as a target over here, then the probability of hitting that target is 0.4, so we just keep that value as a success, and the failure over here is not hitting the target with the 0.6, means that this shooter is not that much professional like a previous one that we talk about it. So at this question we have two actually parts that we should answer to them. One, what is the probability that the shooter will hit on a 5th try? So means that the first, second, third and fourth one should be the failure, so we have 0.6 to the power of 4, and we have one success at the 5th try, so this multiplication lead us to this value 0.05184. And at the second part of the question they ask you to find the expected number of shooting for the shooter to hit the target, and when you just see the word expected numbers, the average number of shooting to get the first hits or something like that, you should calculate the expected value, and this expected value is an inverse of the success, which is equal to 2.5, means that we expected to have a first shoot between the second and the third case when we have the probability as a 4 over 10. So it's clearly can be interpreted by the actually nature things. For example over here the probability of that success is equal to 4 over 10, means that somehow out of 10 cases we have 4 successes, or if you want to find the first successes, then it's going to be at the point 2.5, means that between the second and the third shoots. However, the actually decimal number has no sense over here, so it's better to say that the first expected number of the shooting will be happen in a third one, not at the 2.5. So we should take a look at the last distribution over here that we have it for today's lecture. So let us take a look at the Poisson distribution over here. We have a definition of this distribution as follows. The Poisson distribution is most commonly used to model the number of random occurrences of some phenomenon in a specific unit of space or time. So this is the key of the Poisson distribution, means that it's happened in a specified unit of space or time, means that these things are the characters of the Poisson distribution. For instance, we have some example of a Poisson random variable over here, the number of phone calls received by a telephone operator in a 10 minutes period, or the number of flows in a bolt of fabric, the number of typists per page made by a secretary, means that the mistake in typing that is happened in per similar page by a secretary can be considered as a Poisson character over there. So the definition said that for a Poisson random variable, the probability that x is some value x is given by the formula as follow. So you can see the formula over here. As you can see, the x is infinity, means that the repetition of that random variable could go on to the infinity. And as you can see, because of the nature of the x factorial at the denominator and e to the power of minus lambda t at the numerator, which can convert it to the denominator by the positive exponent, the value of this probability for a big value of x is too small. And as you can see, for a lambda in an average number of occurrence per unit time, origin denoted by t, and for the Poisson distribution we can say that the expected value and the variance is equal to lambda t. Both of them are equal and both of them are equal to lambda t. So for that Poisson distribution, indeed we can use the Poisson distribution for the continuous random variable and discrete random variable. Over here we focus on a discrete case. So you can see some example, and by solving that example you will understand the concept of the Poisson distribution better than this. So we have one example over here. Let's see the example. During a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. So we have the average of happening over here, that is equal to 4 in 1 millisecond. So over here the lambda t, or the value of the average that we have it, is equal to 4. So you should care about this type of the question, that we have the small amount of an information over here. We have the average of the happening, which is given by 4 cases or 4 particles that passing through the counter in 1 millisecond. So the another part of the question is about the probability of something. One of the characterization of this distribution is about the happening, or about the phenomenon that occurred over there in the average of some value enduring of a time or a specific place. Over here we have one specific place, it's a counter that the particle passed through on it, and we have the specific time as well, in 1 millisecond it's happened. So these two actually things determine the type of the distribution over here. Means that with lambda t equal to 4, with one amount of the information that we have it over here, we can describe the distribution. And they ask at the question that what is the probability that 6 articles enter the counter in a given millisecond. So over here you can see that one type of the thing is happen through the time, and it's constant, and it's also determine the average of the happening through the time forever. Means that the number lambda t equal to 4 can be considered for the normal cases forever here. And if x determine the number of the article that passes through that counter in that actually centrifuge or something that we have it over there, then we can denote it by the Poisson distribution. So as I said it, the x denotes the number of number of particles passing through a counter, through a counter. Okay, so by this definition we can say that the x follow the Poisson distribution. Right now, to calculate the probability of x equal to 6, it only needs to follow the Poisson distribution for this case. It will be e to the power of minus lambda t, so e to the power of minus 4, lambda t to the power of x, or 4 to the power of x. Over here x is given by 6 over x factorial, which is 6 factorial. So easily you can find the probability of a given case. So we have one more example over here as well. Let us take a look at this example and see how can we calculate that one. A secretary makes 2 errors per page. The typist error is 2 error per page, and it's happened forever, means that we consider that 2 errors for the average of the error of that secretary forever. So we have one amount of the information again over here, means that the lambda t that we have it here is given by 2 errors per page, so we just put it as a 2 over there. They ask you that what is the probability that on the next page he or she will make 4 or more errors or no errors. So right now again, because the average of the mistakes over there is given by 2 errors per page, so we can consider this value for all values that all errors that we can consider it for that situation. So the probability of x equal to x should follow the Poisson distribution. As I said it over here, in a Poisson distribution we have one information at the question, and that information is about the average of some happening or occurrence in a specific time or a specific place. The specific place over here is the pages of typing, and the time is considered as a time that the secretary do that type of the things. E to the power of minus lambda t means that e to the power of minus 2t should be considered over there, minus lambda t is 2, so it's e to the power of minus 2. Lambda t to the power of x means that 2 to the power of x over x factorial. This is the distribution function over here. So right now at the part A, we ask you to calculate the probability of getting 4 or more mistake or errors. So I'm looking for the probability of x greater than equal to 4. But over here, if you want to calculate that expression, you should calculate it up to the infinity. Means that this probability contains the probability of x equal to 4, or x equal to 5, or x equal to 6, or so on. Means that it started from 4 up to the infinity, plus probability of x equal to 5, probability of x equal to 6, probability of x equal to 7, and so on. So instead of calculating all of this expression, I use the complementary of this probability. Means that I can rewrite that one as a 1 minus probability of having no mistake, probability of x equal to 0, or having 1 mistake, or x equal to 1. So I should subtract it from 1 as well, that value, probability of x equal to 1 as well, and the probability of x equal to 2, and probability of x equal to 3. If I subtract this value from 1, then I have the complementary cases. So it means that instead of calculating that series indeed, we should calculate the complementary parts. It's a practical way to calculate some probability. When you have the series over there, you can use the complementary to calculate it. Right now you can replace the value over here, 1 minus probability of x. Over here, if I put x equal to 0, then 2 to the power of 0 is 1, 0 factorial is 1, so we have 1 over e squared. This is the value for that one. I just shift e to the power of minus 2 to the denominator. For x equal to 1, I have e squared at the denominator again, and 1 factorial is 1, so 2 to the power of 1 give us the value of 2. For the next value as well, e squared should come to the denominator to have a positive power. 2 squared is 4, and 2 factorial is 2. So if I just cancel that value, we have 2 over there again, because 2 squared is 4 and 2 factorial is 2, and after cancelling we have 2. And for the last one as well, we have 2 to the power of 3, which is 8. So we have 3 factorial at the denominator as well, which is 6. e square. Even we can simplify that 8 and 6 at the denominator, and the result is 4/3. So it means that you can cancel these terms and these terms at the denominator to write it as a 4/3. So this is the value for the given cases, and for no errors at the part B, we have the probability of x equal to 0 that we calculated in this case, and it was equal to 1/e square. So the cases of part B was calculated over here implicitly. So another important thing about the Poisson distribution is a property of this distribution to somehow approximate the binomial distribution. So as I said it before, when we have the Poisson distribution, means that some type of the statistical experiment is happened severally up to the infinity times. So if the n at the binomial distribution tends to infinity, means that we have infinity or big number of the terrials, and the probability of success tending to 0, such that the multiplication of them or the expected value of the binomial distribution remains constant, then we can say that the binomial distribution follow the Poisson distribution as well. So we have one example of the cases that we can consider it over here, and after that one I hope that I can solve one more example. So the probability that a person will die from a certain respiratory infection is 0.002. So as you can see, the probability of success over here is given by the small value 0.002. Find the probability that fewer than 5 of the next 2,000 so infected will die. So it means that we have 2,000 of the experiment. We can put the people in a sequence or in a queue over here. So we have 2,000 of them in a queue, means that arterial or n is equal to 2,000. So over here we have 2,000 of the people. So n over here, the small n over here is 2,000, and the probability of passing away over here is constant for all of them. They are independent from each other. I mean, all conditions of the binomial distribution holds true for this case. So from the infection, each of them has the probability of 0.002 to pass away or dying, and for each the probability of getting success is 0.998. So this value is constant for all cases over there. So we can use the binomial distribution to calculate the probability of 5 success, less than 5 success out of 2,000 cases that we have it. But as you can see, the n or 2,000 is too big in comparison with p and the probability, and as you can see, n times p is constant over there. So instead of using the binomial distribution to add these values, we can use the Poisson distribution. Means that we can say that the probability of x less than 4 should follow the Poisson distribution, and instead of calculating the probability of x, look over here, the probability of x normally to be calculated, you can use the actually binomial distribution. For that case, you should calculate the combination of x out of 2,000. It's a big number in a combination indeed. X out of 2,000, and the probability of success over here is 0.002 to over there to the power of the success, which is x, and the probability of failure over here is 0.998 to the power of the remaining cases, which is 2,000 minus x. And instead of calculating the probability with that concept, with that type of the distribution which lead us to the big numbers, we should calculate, we can approximate this value by the following cases. So over here, we first of all we should calculate the lambda t, and the lambda t is as the same as mu over here. Mu over here is equal to n times p. So n times p means that you should multiply 2,000 2000 with the probability of the success over here, which is equal to 0.002, so the value of that one will be equal to 4 there. So the lambda t or the mu over here is 4, so we can calculate it by e to the power of lambda t, or e to the power of minus 4, then 4 to the power of x over x factorial. As you can see, calculating with the second formula is easier than using the first formula. For this reason, we can approximate the value of that binomial distribution by using the Poisson distribution. And for probability of x less than equal to 4, instead of calculating the cases for x equal to 0, 1, 2, 3, and 4, we can replace the x by 0, 1, 2, 3, 4 over here and add all of this probability to calculate the given cases. So I just finished our lecture in this point, and later on we will give you more example about this approximation. Hope that you understand the concept today, and thank you for your attending.